Okay, so in the last class, so we were discussing about the density of states and uh, the distribution, probability distribution of electron uh, in a metallic system. So if you uh, take a schematic band structure of a metal, so we say that this is your energy, and this is the energy band where all these electron states, they are occupied. Okay, so and this energy up to which the electrons bands are occupied is known as your Fermi level, EF. And in order to calculate the number of electrons within the band, so let's say we say this is the N, which is your electron concentration. So that is your number of electrons per unit volume you want to calculate within the band. So what you need to do is you take the density of states and the electron probability distribution, F of E, and integrate it from the bottom to the top of the band. So if you do this integration, so you will get the number of electrons per unit volume or your electron concentration within the band. And so GE is your density of states, which is nothing but your number of electron states or orbitals uh, within energy range E to E plus dE per unit volume. And what is your F of E? This is a Fermi Dirac function, okay, so which describes your probability of electron occupying energy state E, so which we define by this function 1 by 1 plus exponential E minus E of by kV. So which actually will be similar to your Fermi Boltzmann distribution when your E minus EF is much greater than this thermal energy. So this difference, if it is much greater than kBT, so your this Fermi Dirac distribution becomes similar to a Boltzmann distribution. So so this Fermi-Dirac distribution works only for particles. So it is a quantum mechanical probability distribution, and since electron follows this, being a quantum mechanical particle, it follows this Fermi-Dirac distribution. So there is also another kind of quantum mechanical statistical distribution. So just for your knowledge, so it is known as a Bose-Einstein distribution, or BE distribution, which also is a quantum mechanical statistical distribution of particles for quantum mechanical particles. So this Bose-Einstein distribution is like actually the first, which was the mathematical formulation was done by our Indian scientist Bose. Okay, and then he sent his like the mathematical formulation he found, so he sent it to Einstein. So Einstein did a little bit of some modification to it, and then that became a famous Bose-Einstein distribution. Okay, so this is how we can calculate the electron concentration, uh, and this is a mathematical way of uh, calculating it, but we can also understand it from a quantum mechanical, or sorry, from a graphical uh, picture. So let's say if I say I have, so this is again, I'm just drawing, uh, this is my band structure, okay. So this is up to EF, this is let's say 0. Uh, so if I plot G of E as a function of E, okay, so it will be, so the relation mathematical function was G of E was some constant, okay, so it was 8 pi 2 to the power half, then me star by h square to the power 3 by 2 and e to the power half. So the energy dependence is e to the power half, so which is uh, will be like a, a function like this. Now, what is f of e? So f of e, we said at t is equal to 0. So now I'm plotting it again, f of e as a function of e. So at t equal to 0, it will be like this. And when you increase the temperature, so it will be like this. And then as you further increase the temperature, so you have, okay, so this is your T2 and this is your T1. So it is always, what happens is that here T2 is greater than T1. So as you increase the temperature, so you will find more and more electrons. They will occupy states which are the probability of occupying energy states above the Fermi level increases, which is obvious because of the thermal energy. So these electrons, some of the electrons which are on the top of the or close to the Fermi level, so they will jump over and then they will occupy the electron states which are in the uh, which is above Fermi level. Now, if we take the two products, so we will get the electron concentration per unit volume. So now if we take GE and F of E, so how it will look like? So this is G of E, F of E. So it will look like, this is at T is equal to 0. But if you increase, go to another temperature, so you will have something like, okay. So we are plotting it as a function of, again, E. Okay. So at t is equal to 0, it will be like there will be no states occupied on, you'll no electron concentration. There will be no electron concentration above the Fermi level. But as you increase the temperature, so you will have some electrons which will be occupying states above Fermi level, and this is basically what you have. This area under this curve will be your electron concentration per unit volume, so number of electrons per unit volume within the band. So this is your graphical way of looking at the electron concentration in a band. Now, how this is related to conduction of electrons. So we started all this to understand the conduction of electron. So how it is related to the conduction. So now let's look at again. Go back to remember your picture where we plotted energy as a function of momentum. So where if we have taken if we have a one-dimensional crystal, so your E, which is like E square by 2n. So if you plot E as a function of potential, so you will get such a, for a one-dimensional crystal, you will have such a dependence. And what we say that electrons will be occupying, again, all the electron states will be occupied up to a Fermi level EF, and below it all are occupied, above it is empty. But maybe partially also it is also occupied if the temperature is greater than 0 Kelvin. But we also saw that only a few of the electrons which are close to the, so there are all these, there are many possible electron state with different momentum, okay. So all these are electron states with different momentum, and only electrons which are close to the Fermi level, so these electrons will only participate in the conductivity. So when you are applying an electric field like this, the only electrons which is close to the Fermi level, so they will only participate in the conductivity. And the rest of the electrons are basically, they are there, but they are not really contributing to the conductivity of the material. And in terms of momentum, so how we describe it in terms of momentum, we said, so there will be a change in momentum of this electron when the electric field is applied. And what is that change in momentum? Delta P x is equal to tau E, tau E into Px. That is your electric field. So basically your force into your time. So tau is your relaxation time. And what is the energy? So this is this delta E, that is the change in energy of those electrons. Only those electrons close to the Fermi level, they will participate in the conductivity, and they will have an energy change which is about delta E in the change in energy around the Fermi level. So what is delta E? So E is the energy is E x square by 2m, let's say. So that means delta E will be Ex by m into delta Ex. So this energy change of electron close to the Fermi level will be, so now if you substitute this expression delta Px here, so you'll have Px by m tau E X, which you can also write down as m v f by m tau E Px. So your Px, that the momentum that we are talking about is only momentum of electrons close to the Fermi level, and therefore their momentum will be m into Vf. So here m is actually the effective mass. Okay, so m is the effective mass we are talking about. So it may not be the same as the free electron mass. So delta E will be tau E Vf. So this is your Vf is your Fermi velocity. So you can calculate this Vf if you know this from this relation Vf square. This is your EF, the Fermi energy will be equal to half mv F square. That is just the kinetic energy. And what is the current? So the current will be, right, as again going to the classical picture. So it will be N E V. But now since we are saying electrons which are only close to the Fermi level, they are participating in the conductivity. So we say J is equal to NF E VF. Okay, so NF is electron concentration. Yeah, Fermi level. That means those electrons which only gain certain energy, delta E, so those electrons, that number NF, so they only will contribute to the conductivity. And now what is N of F? So it will be again, we can calculate by the density of states at Fermi level, GEF, and the distribution, so the distribution into this is delta E. Okay, so this is the energy. So electron concentration will be N of F G density of states into the energy difference within. So this is the electron concentration per unit volume within the energy range E to delta E. Okay. Where is that? Yeah. So this is the energy range that we are talking about when we calculate the electron concentration. So within E and delta E, so this will be this function G density of states at Fermi level into delta E. And so you can then calculate the current, which is G E of F delta E into E of F. And delta E we just calculated. Delta E is, this is delta E. Okay, so if you substitute that, so you will get a final expression which is something like this: E square VF square tau G E of F so we should also have this electric field. So your conductivity now is, this is your Ohm's law, and the conductivity is given by this expression. Okay, so which is very different from your conductivity in the classical picture. So this is quantum conductivity. So the classical conductivity was N E tau by M. So this is your classical one. So where you assume the electrons are almost free. Okay. So the big difference here, what you see here is like, so most of the behavior will be similar. Only one extra term, what you have here, this density of states at Fermi level, GEF. Okay, so this is your extra term that comes due to the assuming that your particles behaving like a quantum mechanical particle, this density of states, which this concept doesn't exist in the classical physics. But this expression that we are writing here, sigma, is a little bit of overestimation because we assume that the crystal is a one-dimensional. But normally the crystal will be it's a three-dimensional crystal, and assuming that the conductivity is isotropic, so in that case your sigma will be 1/3 of this value. So this is for a 3D crystal. So this calculation what we did is for a one-dimensional crystal. So assuming that the crystal is isotropic. So what is isotropic and anisotropic? Do you know the difference? Anyone? What is the difference between isotropic material and anisotropic material? So isotropic means when I'm saying any material property that I will measure, so it will be the same in all directions. So if I am taking a crystal and I am going along certain crystallographic axis and I am measuring a property, let's say conductivity or resistivity, so it will be the same irrespective of which direction I am measuring, in which direction I am applying the current and measuring the voltage. So the value of resistivity or conductivity will be the same. So that means it will be isotropic. If it is anisotropic, so this value can be different depending on the in which direction I am applying the current and I am measuring the voltage. Okay, so this there will be directional dependent of the material properties. So this can be true for any material property. So you can talk about Young's modulus or its density even, or it can be, let's say like conductivity, resistivity, or the magnetic properties. Okay, all can be isotropic or anisotropic. So depending on the, so some material property can be isotropic, some can be anisotropic as well. So this expression of sigma, the conductivity, actually explains why a conductivity of, so I asked a question in the last class, like if I take conductivity of copper, it is greater than conductivity of magnesium, although copper has one valence electron. So if we assume a just simple classical picture, so we say copper has one valence electron and magnesium has two valence electrons, and assuming the scattering that is happening is similar, so we would expect that magnesium should have higher conductivity because it is contributing two electrons per atom. So that means the concentration should be high. But the reason copper has a higher conductivity is because this comes from this expression. So the density of states at Fermi level for copper is actually greater than that of magnesium. So the number of orbitals or number of energy states that are available close to Fermi level of copper is much higher, and that's why you have a higher conductivity of copper compared to magnesium. Okay, so another, so when we introduce this concept of Fermi level, so there are several use or significance of this Fermi level. So one example I will give, which we will also see later on when we discuss about semiconductors. So let's take a two metals, let's say. So here I am taking example of say a platinum and molybdenum. So I have a platinum and molybdenum metals, and you make a junction of this platinum and molybdenum metal. So what happens when you form this junction, metal metal junction? So you have a metal metal junction. So what could happen? So if I take, now let's look at the schematic picture of the energy band. So this is my platinum. So all these electron states are now occupied up to energy level EF, and this is my vacuum level. So similarly, I will have for the molybdenum, so the picture will be a little different. So, so this is your EF here. So this is your molybdenum. And what is the difference between your vacuum level and the Fermi level? That is your work function I. So this is your work function for Pt. So this is your work function for molybdenum, and this work function is molybdenum is 4.2 electron volt, and phi of Pt, so phi Pt is about 5.36 electron volt. So now when you put them, bring them in contact, what would happen? That you can immediately see, so some of the electrons which are close to the junction, so they will, so these electrons, they are at a higher energy level. So now they will jump to these unoccupied energy levels which are available in platinum. So there will be some, so electrons will jump from molybdenum to platinum. So there will be accumulation of electron on platinum side, and similarly there will be a positive charge will build up on the molybdenum side. And why they would do that? They would do in order to match their Fermi levels. So what happens is basically when you make the junction, so they would like to match their Fermi level. So Fermi level will match when you form the junction, and the picture will look at different, little bit different. So when we do the plotted, so it will be clear to you. So now this is your platinum. Now the Fermi level need to match. So this is your molybdenum. So now you will have a picture something like this. And what happens at the junction? So close to the junction, so you have some electrons which come from the molybdenum side will be here, and similarly this side will have a positive charge accumulation. Okay, and so when the equilibrium will be established, so that means once you have this charge transfer, so it will eventually lead to a electric field. So an electric field will build up, and this electric field will basically, this charge accumulation will stop at equilibrium, and that means this electric field will be strong enough to not allow any further charge transfer from molybdenum side to the platinum side. And this electric field, which is at the junction. So it is actually, you can express it in terms of something known as a built-in potential. So this built-in potential will make sure that when the equilibrium is reached, that means the Fermi levels have been matched, so no further transfer of electron happens. And what is the value of this built-in potential? So this is nothing but your E delta V, which is the energy difference between your work function. So phi Pt minus phi molybdenum. So which is will be equal to 5.36 electron volt minus 4.2 electron volt, which is of the order of 1.16 electron. Okay, so this delta V, which is 1.16 by E, so that much voltage will develop, which is very small, definitely, and so of the order of, as you can see, 1.16 volt. So this much built-in potential will develop at the junction, which will basically make sure that the charge transfer stops when the equilibrium is reached. So this is known as this built-in potential, also known as a contact potential as well. Okay. So whenever you have two dissimilar materials, you make a junction, you put them together, you will always have this contact potential, which will be equal to their difference between the work functions. And remember, you are not changing the work function at all. So the work function of molybdenum remains 4.2, and for platinum it remains 5.3. So it is not like the vacuum level remains the same. So similar, so that's why you will see a jump in the vacuum level at the junction, which normally you don't actually see it because I mean, it is just a energy where the electron will be free. So there will be like a step in the vacuum level of both. So why they want to keep their work function exactly the same. Okay. So when this contact potential develops, when the junction, you make the junction, so it doesn't change the work function. So only the Fermi level they will align or match. And what happens if the Fermi level is not matched? So what happens in case when your delta EF is not equal to 0? So which is like when you just made the junction, so delta EF is not equal to 0. So in that case, so there is a so this delta EF is not equal to 0 means, so you can do some work on the electron, and basically you can move the electron from one point to another. So you can give out, do some external work you can do, and you can move electron from one point to another point. And that is what actually happens until your delta EF is not 0, is 0. So that is why your electron, or we would write like, so you can do the work can be done on electrons, which is known as, it is not a mechanical work, it is a non-mechanical work. Okay. And rather this is known as a chemical potential or electrochemical potential. So therefore this EF sometimes, or EF, is known as a electrochemical potential. So if so now when you have a potential difference, so you can do work. So similarly here, if you have a difference in the Fermi level, so you can do a electrochemical work, which is non-mechanical in nature. So electrical work or a chemical work, let's say, so to say. This is an analogous way to understand that. And in when you make the junction, so you make sure that delta EF will be 0, so that no electrochemical work is done on the electron. So unless you are applying external field or external, like you are giving external temperature or any external like a light, so unless you are doing that, so you cannot do any work on the electron to move it from one point to another point. So you can do work only when you are applying a external, so in presence of an external field or a temperature, like a temperature or heat, or you can say like shining light. So if you apply this externally, so then you can do some this. So you, in that case, you make sure your delta EF will be equal to non-zero, and then that will lead to the flow of electron. Okay, so this is I think a very interesting thing happens when we talk about the phenomena of Seebeck effect. So in what happens in Seebeck effect? So what you have is a metal which is at, let's say, this is the hot end, and then you have a metal which is a cold end, and then this delta T, the temperature difference, leads to a will be proportional to your or will lead to a mismatch in the Fermi level. Okay, so this makes your delta EF is not equal to 0 in the same material. So I'm not taking a different material, even in the same metal. So one end I am heating up, the other end is cold. So in that case, the Fermi level will not match. So delta EF will be 0. That means there is a gradient here, and that will lead to develop a voltage. So the voltage develops, or a voltage difference arises between your hot and cold end, and you can define this effect by a coefficient S, which is known as your Seebeck coefficient, which is given by your dV by dt. So this is your Seebeck coefficient, which is nothing but your potential difference due to the temperature difference. So this concept is used in thermocouples, where you can actually use it as a temperature sensor. Okay, so this is about most of the thing what we described is about metals. So now we will discuss something on semiconductor. So before we move on, any question?
So can you explain Seebeck effect once again?
So Seebeck effect is nothing but, so if you take a metal and somehow you bring, so one end you keep it at a hot or heat, and so that the temperature is high. So one is a hot end and the other one is a cold end at a temperature which is lower than the temperature on the other side. So that means you develop a gradient, right? So temperature gradient. And this temperature gradient will basically will lead to a mismatch in the Fermi level. So delta EF will be 0. So that means it will lead to a movement of electrons. Okay, so there is a electron which, and this is how actually the conduction happens, right? So your electron will move, and now due to this movement, so basically why the movement of electron is taking place, it wants to match the Fermi level, because of the temperature you have the shift in the Fermi level, and that means this there is like a, how do you say, so let's say on this side your here. So if I take the material and I look at the Fermi level, so let's say Fermi level will be somewhere here on this side. I mean, there will be a gradient in the Fermi level. So this is my hot end. This is the cold end. So due to this gradient, so electrons will move, okay, and this conduction happens from the hot end to the cold end. But this will, and unless, let's say, if you keep it as a hot and cold forever, so this electron conduction is taking place. But that also will lead to a voltage which is you can actually measure. Okay, so this delta V that you develop, so you this is a reflection, or tells you, or will be proportional to this difference in the delta EF. Okay, so which is normally expressed in terms of this coefficient S. Okay, known as the Seebeck coefficient, which is basically describes your difference or derivative of the voltage with respect to temperature. And this is so if I so is like this voltage is actually not doing any work, so to say. Okay, so you cannot do any external work using this voltage, or because it is just like a, how do you say, it's like a just due to this electron flow which is different from in different ends, and that leads to this voltage difference. So it is not doing any work, or it will not lead to a flow of like you cannot get an external current by doing that. Okay, so if you are thinking, so if I heat one end and keep the other end is cold, and I have a flow of electron, so and then I put so if I connect a external circuit, so will I get a flow of current? No. So there is no flow of current. I will be equal to 0 if you connect these two ends, because although there is a potential difference, now when you connect this end to the other end by external circuit, so again you are creating a junction here. Okay, so you will create some junction here, another junction here, and the delta V that you generate between the hot and cold, so hot and cold end, so the delta V in this within this material will be, let's say, in the so positive, and the delta V that you generate in the other circuit will be opposite to that, and therefore you cannot get any external current by using this method. So only you can have a develop a voltage difference, which is a difference in the electron energies. Okay. However, if you take two dissimilar materials, so if you take, for example, the famous is like nickel and chromium, so which is normally used for a thermocouple kind of thing. So if you take a nickel and chromium, these two junction, so you can develop a a potential difference which you can actually measure, okay, and then you can use it as a and this voltage difference that you can measure using a voltmeter, for example, so will be proportional to what is the temperature difference, okay, and that you normally calibrate and then you calculate, or you can say what is the temperature of the hot surface. Okay, any other question? Okay, so let's start with this semiconductor thing. How is it? Okay, so it's already time. So I'll then stop here. So in the next class, we will talk about semiconductor or conductivity in semiconductors. How we can understand the conduction in semiconductor materials in terms of this band structures and density of states and the electron distribution, probability distribution. So the same concepts that we have developed, we will use in semiconductors, and you will see that how useful these density of states, the Fermi-Dirac distribution or the electron distribution in general is really helpful in calculating the conductivity of semiconductors. Okay, any other question? Okay, so if not, so then thank you. We'll meet then next week again.